All right, we'll go ahead and get started. Thanks again, everyone, for joining. I am Tim George with Integration Plumbers, and I'm joined today by Jesse Raleigh, also from Integration Plumbers. And we're going to talk a little bit today about fleet management, and specifically using a Rivian API. If you caught the first portion of this, or the first webinar we did, we really kind of went through building out a collector to collect from Rivian vehicles using the API. And today we're going to talk about how we can use that information if we have a whole fleet and we need to manage our whole fleet. So Jesse, I'll go ahead and turn it over to you just before we do just, I guess, just a bit of housekeeping. If you have any questions, feel free to throw them into the Q&A and we can answer those as we go, or we can wait to the end, depending. We like to keep this a little bit conversational. So if we wanted to stop Jesse, I'm sure he wouldn't mind too bad. But feel free to drop it in the Q&A. Don't put it in the chat. Make sure to use the Q&A. All right, Jesse, I'll turn it over to you.
Thanks, Tim. As mentioned, I'm Jesse Raleigh, Head of Engineering, and today we're going to present our approach for developing OpenTelemetry collectors using simulators. Over the next hour, we're going to walk through how we built a fully self-contained Rivian API Simulator in Python, how we use it for simulation testing, and how it ties into a broader OpenTelemetry strategy for electronic vehicle fleet management. If you've been following this webinar series, you'll recognize our example customer, Sparkplug Motors. Let's get started. There's a QR code link in the to the GitHub repository on most of these slides for those who'd like to roll up their sleeves and dig into the sausage making fully. All right. The team at Integration Plumbers has been in the monitoring and telemetry business for a very long time, developing custom integrations and supporting enterprise partners such as Oracle along the way. Our leadership team have been founders or co-founders of several industry-leading companies in both the OTel and broader telemetry markets. Our expertise and breadth of industry knowledge can help you manage the costs and complexity inherent with enterprise-scale OpenTelemetry deployments. Whether you need a full strategy and implementation support, or you are trying to understand if OpenTelemetry is the right solution for your company, we'd love to help. Contact information will be available at the end of the presentation. In this webinar, we will be building upon the foundation laid in the previous two sessions. If you haven't watched the previous two videos, we encourage you to add them to your watch list. We will once again be referencing our favorite example customer, Sparkplug Motors. Sparkplug Motors fields a fleet of 200 Rivian vehicles. Standardizing on Rivian created opportunities to modernize their fleet management strategy, and leveraging the existing OpenTelemetry infrastructure was an obvious starting point. As you can see from the agenda, we have a lot of ground to cover today, spanning from the nuts and bolts of the Python simulation code all the way to the OpenTelemetry collector architecture. We'll wrap up with an engineering review discussing the design trade-offs and future directions. Sparkplug Motors makes extensive use of Python throughout their operations, as we've discussed in previous webinars in this series. Because of the existing prevalence throughout the organization, it made sense to develop our testing simulator in Python as well. So before we get into the simulator itself, let's quickly talk about why Python was the right choice for this project and how the project is structured from a packaging and dependency perspective. Python has a very rich standard library, which enables us to develop internal tools quickly with minimal external dependencies. This provides several benefits, including reducing the security footprint of our simulator. SQLite provides a robust local database solution, allowing us to store application state and configuration data conveniently and efficiently. The match case syntax available in Python 3 and later is particularly well suited for routing GraphQL operations, which we'll see shortly. And of course, Python has first-class OpenTelemetry SDK support, which makes it a natural fit for the observability side of the project as well. We've built this project using UV, a modern replacement for pip and virtual environment. An effective but basic geofencing mechanism was built leveraging the Shapely library, extracting shapes from US government data sources. The application utilizes threads to separate the concerns of serving the API from the simulation and management of system state. Now that we've covered the foundational components, we're going to dig into the implementation of the simulator itself. We'll look at the architecture, how the threads are structured, and how the main entry point ties it all together. The goal here is to give you enough context to understand how the pieces fit So when we get to the deeper code walkthrough, the overall picture is already clear. The Integration Plumbers Rivian API Simulator is a utility we developed to expedite the testing and development of our OpenTelemetry collectors and alerting and management infrastructure built atop it. Our goal was to be able to both verify that our collectors were performing as expected, but also to allow us to inject fault states and simulate conditions at scale. Utilizing the existing Rivian command line tools, we queried real Rivian vehicles logging the returned data. We use this to verify the publicly available but unofficial Rivian documentation for accuracy. In the process of testing and developing our simulator, we also identified some errors in the CLI tool, providing an early indicator of the future utility of the simulator. The subject of threading in Python is always tricky, and we're not going to delve too far into the murky details here. We will, however, explain that for our purpose, this arrangement was well suited. The Flask API service provides data from memory, and the simulation thread generates data quickly but infrequently, resulting in very low potential for contention between the threads. The two functions here, runSim and runAPI, are the entry points into the two threads we create. They share an instance of the Rivian simulator class and the stop event object from the Python threading module. We have to use a bit of non-standard approach to hooking our routes into the Flask app. We're binding the routes to an instance of the API class, which precludes us from using the normal decorator pattern you may be familiar with if you've used Flask previously. In all other ways, the Flask app behaves normally. All right, now we're going to get into the details of the Python simulation code. We'll walk through the key classes that make up the simulator, starting with the fleet coordinator, then looking at the VIN validation, the vehicle state model, the tick loop, and how battery, movement, and geofencing all tie together. If you're following along in the repo, the files we'll be referencing are in the source/IP rivsim directory. The Rivian Simulator class is responsible for the coordination of data simulation and storage. We apply the dependency injection pattern to get a database handler and a geofence object, and then call a few methods to populate our vehicles and users. The load vehicles method iterates over the database records and creates an instance of the simulated vehicle class for each one, which we'll look at next. This is the core orchestrator. Everything else in the simulation feeds into or pulls from this class. There's a complex algorithm that encodes a considerable amount of production data about a vehicle from the VIN number. But for our purposes, we only need the basic validation to ensure that our data was reasonably accurate for simulation. Performing this check at the type level means that any invalid VIN data will fail early and loudly, rather than silently, corrupting downstream simulation state. The live state of all 200 vehicles is managed by the Rivian Simulator instance, persisted through restarts via an SQLite database. We use an additional table to log movements, which are programmatically generated. Each simulation period, in this case 5 minutes, we generate a distance traveled from a random speed applied to each vehicle. From that distance, a new latitude and longitude is constructed within the geofence boundaries of the continental United States. The distance traveled is then used to calculate the battery consumed, which is logged to the movements table and saved to the individual vehicle state. Using basic Python, we pick a random speed between 0 and 70 miles per hour, and from there, we generate new positions and battery states. Each loop we call the apply charging method, which simply returns immediately if the vehicle speed is greater than 0 and the battery has adequate charge. If the speed is 0, it's treated as a parked vehicle, and the apply charging method kicks in to simulate a charging session when the battery level falls below a threshold. This loop runs very quickly, and each iteration advances the simulation clock by 5 simulated minutes, so we can generate hours of activity in seconds. Applying travel and applying charging is just some basic mathematics derived from research into Rivian performance characteristics. We boost the charging rate relative to the documentation for the purposes of our testing. However, this is an area that would present a good opportunity to introduce more realistic charging rates. The real-world Rivian charging behavior is more nuanced, with charging speed tapering as the battery approaches full. For our simulation purposes, a simplified model was more than sufficient to generate the data patterns that we needed for our OpenTelemetry pipeline testing. We've used a very simplistic geofencing strategy, which fundamentally tests to determine whether the current latitude and longitude would be covered by the polygon created from the points representing the United States. We pick a random position based on the distance last traveled, test to ensure that it's not outside the bounds of the geofence, and pick a new random point if the test fails until we succeed. The points used are stored in a simple text file in the examples folder of the project, which can be found on GitHub. The points were extracted from US government data sources provided in a KML format. We opted to reduce them down to a simple text file rather than including a KML library into the project to help minimize the number of extra imports and concerns. We have a light wrapper around the built-in SQLite capabilities, which mostly apply some configuration preferences and handle some basic housekeeping, but it will not be the focus of our attention today. The singleton pattern ensures that both threads share the same database connection, and we've configured SQLite with auto commit mode and relaxed thread checking to support our dual-threaded architecture. If you were scaling this beyond a development tool, you'd likely want to swap in a more robust database layer, but for our purposes, this has proved more than adequate. SQLite in a multi-threaded context does require some considerations, as we mentioned previously. Aside from those considerations, nothing about the database structure is particularly sophisticated. The vehicle movements table in particular serves as an audit log, capturing every position and battery state change throughout the simulation. This is the table that feeds the historical data our OpenTelemetry collectors use for trend analysis. The row factory configuration is a nice quality of life feature from SQLite that gives us a dictionary-style access to row data rather than having to reference columns by numerical index. Now that we've covered how the simulation engine works under the hood, let's shift to the API layer. This is where the simulator becomes useful as more than just an internal tool. The GraphQL API we've built mirrors the real Rivian API surface. So any client that interfaces to the Rivian API can talk to our simulator without modification. We'll walk through the routing, the response structures, and how we generate realistic mock data. Our development approach involves pointing the Rivian command line tool at our own endpoint instead of the real Rivian GraphQL API and running the -- all command. We use the errors listed to add support for every necessary API route until we were able to run the all command without any errors being reported. We started with static return values derived from the RivDocs project and then iterated until we had inserted random or procedurally generated values sufficient to simulate the conditions we were concerned with. Because we began with full coverage, we can easily extend our simulator in the future to cover other use cases or capabilities, as well as introducing fault states in a controlled and testable manner. Routing has been kept simple, with coverage for all of the routes known to the command line utility. Not all routes have data actively simulated, but they will all return semantically correct results. The match case syntax in Python gives us a clean, readable way to dispatch requests to the right handler. Each case maps directly to an operation name that the Rivian CLI tool or a custom client would send, so it's straightforward to trace requests from the client all the way through to the response. Specific routes include the necessary logic to generate valid data, leveraging the Faker library. API endpoints that are not actively used to derive state use less sophisticated data generation methods. The vehicle state response includes over 60 fields, including everything from GPS coordinates and battery level to door lock status and tire pressure. We focused our simulation data generation on the fields that matter most for fleet management, while still returning semantically valid data for the rest. This ensures that our collectors can parse the full response shape without errors, even for fields that we're not actively monitoring. The Rivian API provides a broad assortment of data elements, which can be used within OpenTelemetry to provide reporting and alerts. Ensuring that you begin with clear requirements and objectives can help ensure that you don't collect useless data, slowing down queries and increasing storage costs. We've listed the categories here to give you a sense of the breadth of data available. For spark plug motors, the primary fields of interest are battery, charging, and GNSS data. But having the full set available means we can expand our monitoring scope without having to modify the simulator. The Rivian API associates vehicles with specific users. In our example, we've got 5 fleet managers within spark plug motors who are each assigned 40 vehicles. Because Rivian only allows for 2 API keys per vehicle and drivers consume one with their phone app, we've only stored 1 API key per vehicle in our system. A future target for simulation are the charging sessions. Spark Plug Motors has plans to install EV charging stations at most of their physical locations, and incorporating them into the OpenTelemetry deployment will continue to provide a holistic view of the fleet. The data returned here mirrors what a real charging session looks like, including power delivery rate, state of charge, and elapsed time. Once the charger infrastructure is in place at Sparkplug's facilities, we'll extend the simulation to model charging behavior more dynamically with sessions that reflect the time of day and vehicle usage patterns. The Faker library makes it trivial to generate semantically valid data that is decoupled from your real customer or company information. This makes it ideal for creating testing simulations against systems that contain sensitive information, aside from it being convenient. One of the underappreciated benefits of using Faker is that it prevents your test data from becoming a liability. We've seen cases where teams accidentally hard-code real customer information or API keys into their test fixtures. Faker eliminates that risk entirely, generating fresh, realistic data on every call. Okay, so we've spent a good amount of time on the technical details of the simulator, so let's step back and talk about why you'd want to build something like this in the first place. The benefits go well beyond just having a testing tool. Simulation testing changes how your team develops, how fast you can iterate, and how confidently you can deploy changes to production. Simulation testing grants you the ability to control the state of external dependencies that you don't actually control. By mocking the APIs and services your company depends upon, you can ensure that your own systems handle error states and service outages in a predictable way with appropriate alerts and logs. You are also free from any constraints that your service providers may place upon you, such as rate limits or other thresholds. The simulated environment is isolated from your production systems and as a result provides containment against unexpected side effects. You can also control variables that would otherwise be impractical, such as timestamps of events in the system. You can simulate months of activity in minutes when you can control the clock itself. Simulations also present the possibility of scripting event sequences so that you can reproduce and test to your satisfaction. This is one of the most powerful advantages of simulation testing. Consider something like battery reaching 0% while the vehicle is in transit. In the real world, that's an expensive and possibly dangerous scenario that you just can't trigger on demand. With our simulator, you can set that state directly in the database and observe exactly how your monitoring systems respond, repeating the test as many times as you need until you're satisfied with the outcomes. This comparison really speaks for itself. Without a simulator, getting a new developer productive against the Rivian API can take days or even weeks between requesting API access, configuring credentials, and getting a test vehicle provision. With the simulator, it's as simple as cloning the repo and running Python main py. Everything needed is right there, self-contained, with 200 vehicles ready to go. The kind of onboarding speed is a significant competitive advantage, especially in a fast-moving development environment. Let's move on to how simulation testing works in practice. We've talked about what the simulator does and why it's valuable. Now we'll discuss how you actually integrate it into your development and testing workflows, including CI/CD pipelines and scenario-based testing. These patterns are applicable well beyond our Rivian example. Any team building integrations against external APIs can benefit from this approach. Simulation testing is distinct from both mocking and stubbing. It's worth understanding the differences clearly. The key distinction is that our simulator models actual behavior. Vehicles move, batteries drain, charging occurs over time, and state changes propagate across API calls in a realistic way. When your code calls get vehicle state, it gets back data that has been shaped by the simulated physics of the system, not just a hard-coded JSON blob. This means that your integration tests are exercising real data flows, which catches a category of bugs that simpler testing approaches would miss entirely. To put a finer point on the comparison, stubs are fast and simple, but they tell you nothing about how your system behaves when state changes over time. Mocks add call verification, which is great for unit tests, but they still return canned data. The simulator sits at the highest fidelity level. It maintains vehicle state in a real database, battery levels change based on simulated driving patterns, and GPS positions are constrained by a real geofence polygon. The trade-off is complexity, but the bugs you catch at this level of testing are the ones that would otherwise only surface in production. Integrating the simulator into your CI/CD pipeline is straightforward. You start the simulator as a background service, run your integration tests against localhost on port 5050, and tear it down when you're done. Because there's no network dependency and no external API to contend with, your pipeline is deterministic. Tests don't fail because a third-party service had an outage or your internet dropped, and you're never blocked by rate limits. You can also seed specific vehicle states before each test run, which gives you full control over the test conditions and make your assertions reliable and reproducible. Here are a few concrete test scenarios to illustrate the approach. For a low battery alert, you seed a vehicle at 5% charge and verify that your monitoring system fires the correct notification. For a charging session lifecycle, you start at 20%, run the simulator forward until the vehicle hits 80%, and verify that the UI and dashboards update accordingly. For geofence monitoring, you can just set the vehicle's position to somewhere outside the boundaries and make sure that your logic triggers appropriately. Each of these would be extremely difficult to test against the real API, but with the simulator, they're trivial to set up and repeat. Now we're going to shift gears and talk about the broader challenge of EV fleet monitoring. We've shown you how to build and test against a simulated API. The question now is, what does production monitoring architecture look like, and why is it such a hard problem to solve? EV fleet monitoring is fundamentally different from traditional infrastructure monitoring. Every manufacturer has a different API. Rivian uses GraphQL, Tesla exposes a REST API, Ford has Ford Connect. The data formats vary, the update frequencies differ, and over-the-air updates can change the shape of the telemetry data without warning. On top of that, vehicles are mobile, intermittently connected, and crossing network boundaries constantly. Traditional APM tools were designed for stationary servers sitting in a data center, not for a fleet of trucks driving across the country. That's why a purpose-built observability approach is essential. Let's talk about scale for a moment. A single Rivian vehicle exposes over 60 telemetry fields per request. At 5-minute polling interval, that's 700 data points per hour per vehicle. Scale that to a 500 vehicle fleet, and you're looking at 360,000 data points per hour. And that's before you factor in charger sessions, trip planning, and movement logs. This is a classic observability problem. You need fast processing latency for alerting, but you also need cost-effective historical retention for trend analysis. Getting both right requires deliberate architecture choices. Schema evolution is what I call the silent killer of monitoring pipelines. Rivian regularly pushes over-the-air updates that can add new fields, change field types, or restructure endpoints. If your monitor pipeline has a rigid schema, it breaks on the first unexpected field. This is exactly why we advocate for OpenTelemetry's attribute-based data model. It was designed from the ground up for extensibility. New fields become new attributes without requiring changes to your pipeline, your collectors, or your dashboards. If you take one thing away from this section, it's that your telemetry system needs to be designed for change from day one. With the challenges laid out, let's talk about the solution. OpenTelemetry is the answer to nearly every problem that we just described. And in this section, we'll walk through why it's the right fit and how the 3 pillars apply to fleet management and what the collector architecture looks like. If you're already using an observability platform, there's a good chance that OpenTelemetry can integrate with it directly. OpenTelemetry is the cloud-native computing foundation standard for observability telemetry. It's become the clear industry consensus. The key advantage for fleet management is vendor neutrality. You instrument once, and you can export to Prometheus, Jaeger, Datadog, Splunk, Oracle Cloud Infrastructure, New Relic, or any combination of those. The attribute-based data model handles schema evolution naturally, which directly addresses the challenges we just discussed. And with over 1,000 contributors and proven production deployments at massive scale, this is not an experimental technology. It's the foundation of modern observability. Let's map the 3 pillars of observability to our EV fleet use case. Traces let you follow a request from your application through the GraphQL resolvers all the way to the vehicle state database. This is invaluable for pinpointing latency issues or debugging failed authentication flows. Metrics give you the fleet-wide view, battery state of charger distributions, charge session durations by charger type, geofence violations per hour per region. This is your operations dashboard. And structured logs correlated with trace IDs give you the vehicle state change audit trail that compliance and operations teams need. All 3 pillars working together give you a complete picture of your fleet. The OpenTelemetry collector is the architectural centerpiece of the fleet monitoring pipeline. It sits between your vehicle data sources and your observability backends, functioning as a fleet-wide telemetry gateway. The receiver accepts OTLP data from your application or custom receivers for vehicle APIs. Processors handle filtering, batching, sampling, and enrichment in the pipeline. Exporters send the data to one or many backends simultaneously. For fleet-specific use cases, you can batch vehicle state updates to reduce backend write amplification, sample high-frequency GPS data, filter out unchanged fields to control storage costs, and route critical alerts directly to PagerDuty or your incident management systems. EV technology moves fast, and your monitoring infrastructure needs to keep pace. Today, Rivian uses a GraphQL API. Tomorrow, they might add gRPC streaming. Today, you're capturing 60 vehicle state fields. The next OTA update might add 20 more in new categories. OpenTelemetry insulates you from all of these changes. You can swap exporters without changing your instrumentation code, add new attributes without breaking existing dashboards, and route different signal types to different backends. Your instrumentation investment survives vendor switches, which is critical when you're building infrastructure that needs to last for years. One of the most compelling features of the OpenTelemetry Python SDK is the auto-instrumentation capability. For our Flask-based simulator, it's essentially one line of code. You install the Flask instrumentation package, call Flask instrument app, and every HTTP request automatically gets its own span with method, route, and status code, as well as latency. Each GraphQL operation gets tagged with the operation name attribute, so you can trace specific API calls end to end. You can also instrument the SQLite queries, giving you visibility into the database layer. The simulator becomes an observability testbed with minimal code changes, and you can validate your entire OTel pipeline before you ever connect to real vehicles. Okay, we've covered a lot of ground individually, so now let's bring all the pieces together. In this section, we'll walk through the end-to-end pipeline, a custom Rivian collector that pulls the API, transforms the data into OpenTelemetry metrics, and exports it to your observability platform. This is where the simulator really proves its value. The end goal of this entire effort is a custom OpenTelemetry collector pipeline, purpose-built for Rivian fleet data. The custom receiver pulls the Rivian API, or our simulator, on a schedule. It calls getVehicleState for each VIN in the fleet and converts the vehicle state fields into OpenTelemetry metrics with semantic attributes. GPS positions are emitted as trace spans with latitude and longitude attributes, giving you both real-time position data and historical route tracking. A processor enriches every single fleet signal with fleet metadata, division, region, driver assignment, and so forth. And the exporter sends it all via OTLP to the observability platform of your choice. The simulator lets you build and test this entire pipeline on your laptop before it ever touches a production vehicle or even your data center. Here's the concrete mapping from the Rivian API fields to the OpenTelemetry metric names. Battery level becomes a gauge called vehicle.battery.level, measured in percent. Distance to empty becomes vehicle.range.remaining, measured in kilometers. Odometer becomes a counter, and speed and cabin temperature become gauges. Every metric carries a consistent set of attributes, including VIN, fleet ID, division, vehicle model, and region. This is what gives you the ability to slice and dice your data in the dashboards down the road. The resource attributes identify the service itself. This mapping is fully testable against the simulator, which is exactly how we validate it before production deployment. Here's the step-by-step workflow for testing your OTel pipeline end-to-end. You start the simulator, point your collector at localhost, run the simulation forward for several thousand ticks to generate a realistic volume of data, and then verify that the metrics appear correctly in your observability backend. From there, you can build dashboards, create alerts for critical conditions like low battery or geofence violations, and run load tests with all 200 vehicles to validate that your pipeline can handle the throughput. Then you can introduce failure scenarios, database errors, malformed API responses, network timeouts, etc. All of this happens without touching a single real vehicle, and you can repeat the entire cycle as often as you need. Now let's wrap up with an engineering review. Every design decision involves trade-offs, and we want to be transparent about the choices we made, what worked well, what the limitations are, and what we'd invest effort in next. This is the important context for anyone evaluating whether to adopt this approach or looking to extend the simulator for their own use cases. Let's walk through some of the key design decisions in the simulator. The singleton database pattern ensures that both threads share one connection, which is simple and effective for our use case. The dictionary-based state model gives us flexible schema mapping that mirrors the database columns directly. Tick-based simulation with 600 seconds elapsed per tick gives us deterministic time advancement, which is important for reproducible testing. The random speed generation using a uniform distribution between 0 and 70 gives us a reasonable approximation of real-world driving patterns without overcomplicating the model. And the match case routing is clean and extensible, though it does require Python 3.10 or better. Now for some limitations. The SQLite thread safety configuration works, but isn't optimized for high concurrency scenarios. There's no WebSocket support, which means we can't simulate push-based real-time data streams. The charger session data is currently static rather than evolving with the simulation. Right now, authentication always succeeds by design, which is useful for testing, but it means we can't test authentication failure scenarios without some modifications. Each of these represents a potential area for future development, and we've designed the architecture to accommodate these extensions without major refactoring. For Sparkplug Motor's current fleet of 200 vehicles, SQLite performs well. But if you're looking at scale to 1,000 or more vehicles, you'd want to consider Postgres or TimescaleDB for the persistence layer. Adding a Redis caching layer for vehicle state would support real-time dashboard rendering at scale and decouple some of your concerns. For a production simulation environment deployment, Kubernetes gives you horizontal scaling. On the OpenTelemetry side, you'd deploy the collector in gateway mode with load balancing to handle the increased throughput. The key point is that the architecture is designed to grow from laptop to production deployment without requiring a fundamental redesign. We've containerized the simulator using Docker, which makes deployment and sharing across the team significantly easier. The Docker image is based on Python 3.14 Slim, keeping the footprint small while providing everything the simulator needs to run. The key design decision here was to use a volume mount for the examples directory, which contains both the SQLite database and the geofence points file. This means the simulation state persists across container restarts, and you can reset the database simply by dropping the container and replacing the file. For CI/CD pipelines, this is particularly valuable. You can spin up a fresh simulator instance as a service in your pipeline, run your integration tests against it, and tear it down when you're finished. No Python version conflicts, dependency issues, or environment drift between developers. Here, we're looking at the configuration files that make the Docker deployment work. The Docker file follows a straightforward pattern. We start from a slim Python base image, install UV for package management, copy in our project files, and install dependencies. The volume declaration for the examples directory is important because it signals that this path is meant to be externally managed. The Docker compose file is intentionally minimal, one service, one port mapping, one volume mount, and less stopped restart policy, so the simulator comes back up automatically if it crashes or the host reboots. If you need to run the simulator without compose, we've included the equivalent Docker build and Docker run commands in the project documentation. The key thing to remember is a volume mount for the examples directory, which ensures your SQLite database and geofence data are available and writable at runtime. With the Docker image already built and tested, the natural next step is deploying to Kubernetes for production-grade orchestration. Kubernetes gives us several capabilities that Docker Compose alone cannot provide. Automatic restarts, rolling updates, horizontal scaling, and health checking are all built into the platform. The persist volume claim is critical here. Without it, your SQLite database and geofence data will be lost every time a pod restarts. The PVC ensures that the examples directory is backed by persistent storage that survives pod lifecycle events. The liveliness and readiness probes are configured to hit the GraphQL gateway endpoint. If the simulator becomes unresponsive, Kubernetes will automatically restart the pod. The readiness probe ensures traffic is only routed to pods that are fully initialized and ready to serve requests. For teams already using Kubernetes for their OTel collector deployment, running the simulator in the same cluster simplifies networking and reduces the operational overhead of managing separate testing environments. Here, we're looking at the individual Kubernetes manifest files that make up the deployment. The deployment YAML is the core resource. It defines the pod template with our IP rivsim container image, sets the replica count, and configures the volume mount for the examples directory. Service YAML creates a stable network endpoint within the cluster. For most development and testing scenarios, a cluster IP service is sufficient. If you need external access, you can switch to load balancer or add an ingress resource for domain-based routing. The config map is where we externalize simulation parameters. Rather than rebuild the Docker image every time you want to change the tick interval or fleet size, you update the config map and restart the pod. This is particularly useful when running the simulator in different environments with different testing requirements. We've also prepared a Helm chart that templatizes all of these manifests with environment-specific values. This allows you to deploy consistently across dev, staging, and production namespaces using a single chart with different value files. Security is always a priority, and the simulator was designed with a clear separation between development safety and production recommendations. On the simulator side, no real credentials are stored. All personal data is generated by Faker, and the SQLite database is git ignored. The entire tool runs on local hosts with no outbound network calls. For production deployments, we recommend Vault for credential management, mutual TLS between the collector and your observability backend, role-based access control on dashboards, PII scrubbing within the OTel pipeline itself, audit logging on any vehicle commands, and network segmentation for fleet data. These aren't just suggestions, they're requirements for any enterprise and fleet management deployment. To summarize what we've covered today, the API Rivian simulator gives you a complete, realistic test environment for developing fleet management infrastructure. Python, Flask, and SQLite deliver a self-contained solution with zero external dependencies. Simulation testing catches integration bugs that mocks and stubs simply cannot. It accelerates development dramatically by eliminating external dependencies from your workflow. EV fleet monitoring demands flexible, vendor-neutral observability approach, and OpenTelemetry is purpose-built for exactly that. The collector architecture maps naturally to fleet telemetry pipelines. Most importantly, build and validate your entire monitoring stack before connecting to real vehicles. The simulator makes that possible. This concludes our presentation. Thank you for your time today. If you'd like to explore how OpenTelemetry can improve your fleet management operations, or if you're interested in simulation testing for your own integrations, we'd love to talk. You can reach out to our team through the contact link on screen, or you can contact with me directly. We offer workshops, guided proofs of concept, consulting engagements tailored to your need. Thanks again. I'm going to hand it back to Tim.
Yeah, thanks, Jesse. Just a couple of quick questions came in. Just wanted to ask you those real quick here. So first of all, Ken Brower is asking, how do Rivian's device enrollment policies, such as the 2-phone limit, impact the ability to deploy these collectors at scale, or does that affect them at all?
They were a core consideration in our approach of developing a simulator. So there are some consequences that are tied to those two API keys. For example, if you are too aggressive in your interactions with the API, you can find that API key locked, and that requires a call to tech support with Rivian to return it to service. And as a result, you have to be very cautious in what you send and how often you hit the API.
Gotcha. One last question from Mike Helmus. I think we covered this a little bit, but he's asking about how does the system determine if a vehicle is currently offline or out of service?
We depend upon the API to tell us that. So the API itself has a sense of when it last spoke to a vehicle, and at a certain point, it puts it out of service. So we can either utilize the API state itself, or we can create alerts based on the last time we've received a response and be more aggressive than the API would be.
Awesome. Yeah, I don't see any other questions coming in at the moment. If anyone has any, feel free to drop in the Q&A. Otherwise, as Jesse mentioned, visit us at integrationplumbers.io. We can see how a custom OTel collector could potentially help you in your projects that you're currently ongoing. If nothing comes in, I don't see any questions coming in, so we'll end it here. Thanks everyone for joining, and hope everyone has a great rest of the day. And thanks, Jesse, to you for presenting today.
My pleasure.
All right, bye-bye.